Jin from National University.
Hi, my name is Seong Jin KIM from NTHU. The title of this presentation is like this. Today I'm going to talk about infrared number counts using JWST data. So the number count or source count is simple and straightforward because source count is actually counting the number of sources in a specific flux range or flux bin. So it's quite simple. But it delivers quite important and evolutionary meaning in observational cosmology. Because even though the number counts are obtained from the 2D surface on the sky, it is actually accumulated and projected results on the sky from all the infrared sources over the whole redshift range. So that's why we're trying to do this. And yeah, so since July, the early science data of JWST became available. So as presented previously, our student Jimmy, one of our paper actually using this JWST data published last week. So it, as you already heard of this, it gives brand new source count in the mid-infrared using JWST data. And you can also check this. This is another source count paper. So mid-infrared source count, or for example, 15 micron source count have been carried out for so long, 20, 30 minutes. But the detection limit at the time was about only a few millijensky, but it got deeper and deeper a little bit and reached down to below 0.1 millijensky, thanks to the Akari and Spitzer telescope. But in this paper, in our paper, the result is amazing. So we reached down to micro-Jansky level, and it gives 100 times faint galaxies compared to the Akari sources. So the sources contributing to the infrared background in the previous infrared works actually now result into individual sources. So it's amazing. And also, you already saw the couple of models here. These are just predictions from the previous works. And it shows quite it looks good, showing quite a good agreement between the models and JWST data point. But definitely, it's time to update this older model, right? Using this 100 times fainter galaxies to study evolution. But someone might ask question, evolution? Just counting numbers? How could just this number counts can give you the evolution? You don't even know the redshift information, right? But this is kind of fully data-oriented way to study evolution. However, in reality, sometimes it's really difficult to get all the data you want to have, right? But on the other hand, in the model approach way, we may be able to try to estimate the evolution or history of the evolution or something like that. Which means we have to take some kind of assumptions. So in this way, what kind of physics can we learn? What would be exciting? So let me explain a little bit about this. So to model the source count, so first we have to know the distribution of the galaxies in the local universe at the redshift 0. In this case, so many observations have given accumulated information about this. So mostly we already know the functional shape of the luminosity function. So actually we can just choose and take it. And the population mix, in this work we tried 5 different types of galaxies, but galaxies are roughly divided into 3 types, right? Star-forming galaxies, AGN, and a mixture of those two, which we call composite. But star-forming galaxies can be divided into just normal star-forming galaxies and starbird, and AGN can be divided into type 1 and 2. So we decided to test 5 different types. So spiral we took one of these spiral, for example, spiral type C for normal star-forming galaxies, and RP222 for starbirds, and Mark 231 for composite type of galaxies, and AGN type 1 and 2. And then we have to make these galaxies evolve. So we need some rules of how those galaxies evolve. So this part is important because everything will be ruled by some regulations. So evolution parameters are here. And then after we evolve these galaxies, all the luminosities of these galaxies will be converted to flux density in the observed frame. This is how we count the number of galaxies as a function of observed flux densities. So we need some moving volume information and calculation. And we going to compare this number count with actually observe the number count where our JWST data, so 100 times fainter galaxies are included here. So we need to compare these two. And this is actually a fitting procedure. We need some technique and trial and error. And sometimes we have to go back to here to find better parameter combinations. So based on some luminosity, local luminosity function, and population mix, and some evolutionary parameters, we can make galaxies evolve like this and try to reproduce the observed number count like this. So our work can be divided into these 4 steps. So even without redshift information, maybe if we can do this, we can study evolution. So this slide shows step 1 and 2. This is 15 micron local luminous function. Actually, we took this from the Lupinonius graph. And this is step 2. So most important assumptions are actually these equations. These equations rules how the luminosity and densities will evolve as a function of redshift. But most importantly, these 4 parameters are most important. AL, L5, and kappa, lambda. These 4 parameters determines the shape of the evolution. So in this work, we are trying 5 different types of galaxies. So 5.5 times 4. So we're going to test the 20 evolution parameters in total. And then these local luminosity functions will evolve as a function of redshift like this. And then in step 3, the number density will be converted to the actual number count using comoving volume. And then the luminosity will be converted to the observed flux density in the observed frame. And then we integrate all the luminosity function, and then this is our integration results. And then we sum up everything. This thick gray line is a total integration from all the individual different type of galaxies. And step 4 is fitting, right? So this image is taken from the source code paper, and this is our result. So we changed a little bit like this. So this red curve is our best fitting model, and actually this dark red curve is contributed from each type of galaxies, spider and starburst, and the others. And then previous parameters was used as an initial value, and we got new evolution parameters. So now we have new, this is new evolution parameters, and determines all things in the evolution. So using these new evolutionary parameters, I think we try to construct the infinite luminosity density. This is actually cosmic star formation history, and also we're trying to construct the black hole accretion history. Actually, this we tried 5 different types of galaxies. The reason is we wanted to try to history of the universe in these 2, star formation history and black hole accretion history. So the black hole accretion history was derived from Asian type 1, type 2, and composite galaxies. And then we try to compare optical or UV data. Basically, grouping is paper like this, but it didn't change much. So this is summary of this work. We used the JWST early science data and the number counts. We used 100 times fainter galaxies and model a best way to interpret and to physics. To learn the physics, we use the model approach to that. And we try to reproduce source count, and then we got the new evolutionary parameters fitted to faint JWST galaxies. Yeah, and finally, we were able to update history of the universe. That's all.
Great. So, questions or comments? Yes, please.
Right. Thanks for your talk. So this is a number count in IR wavelength, right?
Yes.
And so I think there are many other researches about number count in different wavelengths,
Yes.
including maybe microwave or something. So if you have any different discover or some new discover different from other wavelength number count.
Actually, we just decided a new evolution parameter just by using 15 micron wavelength. But you can use both or 3, 4, or 5 bands. So I think maybe next step would be fitting to multiple bands simultaneously, and I think the evolutionary parameters will be slightly changed.
So these galaxies, JWST detected galaxies, and then 100 times fainter than previous bits or something. So it's mostly not detected in millimeter or any other wavelength. So the one possibility is we can use the background fluctuation from millimeters, but that's the only constraint.
Okay. More questions? Yes.
If I
understand correctly, the first step is to use the local luminosity function.
This one, yes, local.
So this
First
is-
step is local luminosity function.
So this one is fixed, or this can also be changed in the model?
Yeah, that's right. It actually depends on what kind of luminosity function we choose.
So when you derive the new evolutionary parameters, you fix the local.
Yeah, we just fixed this one.
So how valid is that assumption?
In the local luminosity function, I think. But this luminosity function is based on all the previous observations, in, basically from Spitzer, Akari, Herschel, all these observational data, and then this local luminosity function is determined. So it's one of the widely accepted luminosity functions. So that's why we choose this luminosity function.
Okay, maybe one more question. Yes, please.
Yeah, I'm just curious whether or not there's any degeneracy in the model parameters.
I'm sorry?
Whether or not there's any degeneracy in the model parameters, because your observational constraint is just the number counts, right?
Yeah.
Yeah, I just wonder, because you are several parameters, so when you do the fitting, whether or not there's some degeneracy that can, like two sets of parameters can reduce the number counts.
That's right.
There probably is some. He hasn't checked, but we are going to check later. And then I just the other point is that it's not just it's using 15 micron. As other papers showed, we have JWST has many bands, so we have some more additional constraints, a little bit more.
That's what I thought just before.
Thank you.
This is just one band, right? So we will try to get
Is your mic?
five, 6 bands simultaneously.
Thanks.
So then maybe it's going to be resolved.
Okay, great. So I think we should move on. Let's thank Seong Jin again. And our next speaker